We have seen in a previous set of notes that R uses an iterative numerical procedure to find the maximum likelihood estimates of our regression parameters, our betas. What that basically means is that R comes up with some initial estimates of the betas, then it looks to improve them in a iteration through using a numerical iteration or algorithm, let's say. Then once these new estimates are found, they are compared to the previous initial set of estimates. If they are very similar, what that means then is that you're simply done. You could not actually improve upon those estimators. If instead they are not near each other, then R is going to do another iteration of its numerical procedure to find potentially better estimates of your betas. Once again, these new estimates are compared to the previous iteration's estimates. If they are close, you're done. You are what would be referred to as you have converged. Otherwise, this iterative procedure keeps on going and going and going until you get to a point where these estimates do not change it anymore, or you reach a maximum number of possible iterations. So this set of notes here examines that iterative numerical procedure a little bit more, so we can see how R makes a judgment about convergence, and also we will talk about what are particular cases where convergence might not be reached. Okay, so what R does, instead of comparing the estimates of the regression parameters directly, it computes the residual deviance, which of course then would be a function of your beta hats. It computes that at each iteration of this iterative numerical procedure. Then it compares the residual deviance at each iteration. Once you get to a point where the residual deviance is not changing much, then R says, okay, we have converged, we can stop. We have found the maximum likelihood estimates. So let's let capital G within the superscript in parentheses K represents the residual deviance at iteration K of the iterative numerical procedure. Then R uses the following criteria then to decide upon convergence. It looks at the residual deviance at iteration K, compares it to what it was for the previous iteration, finds the absolute value, so that looks at how close they are to one another, and then the denominator in this expression basically takes into account the relative size of the residual deviance. Then R compares it to some pre-specified small number close to zero, we'll call it epsilon. If this quantity is less than epsilon, R says you're close enough with your residual deviance, you have converged. Otherwise, the iteration process keeps on going until convergence is reached, or a maximum number of possible iterations that was pre-specified is reached. Okay, so you can specify some of the stuff that you see up here in this convergence criteria, you could say. In particular, there is an argument in GLM that's called epsilon. That's what corresponds to that epsilon right there, that Greek letter. And by default, R uses a small number close to zero, that's positive, 10 to the negative 8th power as its epsilon. The maximum number of iterations that R does by default is 25. You can change that by using the maxIt argument in R. And if you want to see the process that R is using in terms of what is the residual deviance at each iteration, you can say trace equal true in GLM to actually see it. So let's take a look at how we can examine this more closely relative to the place-kicking data set. So here in my tin, oops, there we go. I've already read in my data set, my place-kicking data set. I'm just going to use distance as the only explanatory variable to estimate the good, the success or failure of the place kick. Now here's my GLM code. The things that's different from what we've done before is what I have highlighted here. I'm going to say trace equal to true so I can see the iterative history. I'm going to make epsilon much bigger than what it would normally be. And then I'm going to allow myself to have up to 50 iterations. So let me go ahead and run that segment of code. And if I specify summary mod.fit, you'll notice that at the very bottom it says the number of iterations that it took for this procedure to converge, 5. So if I come up here, trace equal true produced this information that I've highlighted. This gives me my G at each iteration. So for example, G with a superscript 5 is 775.745. This very last iteration here is where convergence was achieved, iteration 5. Let me come back over here to my Word document. So we can go ahead and calculate that if we wanted to. So what I can do is make this G5, G4, go through the calculation. Notice we get 1.3 times 10 to the negative 7th power. That is less than 0.0001, so that's why R said convergence was reached. And in fact, one could actually go inside the mod.fit object to see the converge component, and notice it said true, that indeed it did work. Now for iteration 4, if you were to calculate the same quantity now, but using G super 4, G super 3, do this on your own, you will get 0.00012. That is larger than the epsilon, so that's why a 5th iteration was needed. If you were to change max it to just simply 3, then R will say, uh-oh, convergence has not been obtained. In this particular case, you would not want to use then the corresponding estimates because those estimates are continuing to change. So at iteration 3, if you just use those estimates, the model that you get, and thus the interpretation of your model that you get, will be different than if you were to allow then the procedure to actually converge. Okay. Notice also says glm.fit there. Basically what the glm function does, it actually calls another function called glm.fit that actually does the iterative numerical procedure. So that's why that warning message was written in that way. So what should you do if convergence is not obtained? Well, first thing, try a larger number of iterations. Simply see if that helps. If it doesn't, then the reason might be is that there might be some fundamental problem with your data that's causing it. Probably the number one reason for non-convergence with logistic regression models is because of something called complete separation. What that means is suppose you have a simple situation where you have one explanatory variable. This explanatory variable, let's call it x. When x is less than or equal to 5, let's say y is always 0 in your data set. Then when x is greater than 5, y is always equal to 1 in your data set. Notice how the value of x is what separates out the y equals 0s from the y equal 1s. That's called complete separation. And in that particular case, when you have just this one explanatory variable, your beta hat 1 will be positive infinity, which isn't good, to have an infinite value, meaning that basically beta hat 1 for each iteration is going to just keep on increasing without bound. Now, in this kind of a situation, when something like this occurs, very often R will print a message such as this: fitted probabilities numerically 0 or 1 occurred. What that means is that your pi hat ends up being 0 or 1 for some observations. We'll look at shortly why that happens under complete separation. But I just wanted to point it out here that you may actually get a warning message that's different from this, where of course when you see that, it says, well, convergence wasn't obtained. But you may actually get convergence, or R will say convergence has occurred, even though it hasn't. But one message that might tip you off that, uh-oh, R is telling me something wrong, is when you see something like this. Now note that this is not a perfect indication of non-convergence. It could just be within your data set. You just simply have some scenarios corresponding to your explanatory variables where you have very high probabilities of success or very, very low probabilities of success. So for example, let's think of the place kicking data. Suppose we have some 100-yard field goals that are attempted. Now, in football, making a 100-yard field goal has never been done before. It probably will never be able to be done. It's just too long. And so the estimated probability of success for those particular, let's say, observation, let's say that they were actually tried at 100 yards, they should have an estimated probability that's very, very close to zero because of the nature of the problem. And R would still then produce this message here, but that wouldn't be something to worry about. So if you are unsure, though, what is going on here with this message, what you can do is look back in your data to see if it makes sense, for some cases to have an estimated probability of 0 or 1. You could also decrease your epsilon closer to 0, meaning essentially a stricter convergence criteria, and see if your estimated regression parameters change with the stricter case. If they do, that says you had not actually achieved convergence before because the beta hats are still changing. Okay, so let's take a look at an example that corresponds to complete separation. My code's in my program non-convergence.r. This is a situation that actually I previously described. I create a data frame called set1 where if x is less than or equal to 5, y is equal to 0. If x is greater than 5, y is equal to 1. So let's go ahead and estimate this model using the default epsilon, using the default maximum number of iterations. So to estimate this model, my response is y. My explanatory variable is x1. I'm going to say trace equal true here so that we can see the iterative history. And so eventually we get to iteration 25 with all the printing, and then R says this, uh-oh, algorithm did not converge. But you can still pull out the corresponding beta hats, you could say, from mod.fit. You should not use those beta hats because if I were to continue here, I would expect these beta hats to change because convergence has not been reached. The plot on the left here shows what's actually going on, why non-convergence occurs. So on the x-axis here, I have values of x1. On the y-axis, I plot the corresponding values of y. Again, if x1 is less than or equal to 5, y is equal to 0. If x1 is greater than 5, y is equal to 1. And we see that with those plotted points. And also what we see here in red is the actual estimated logistic regression model using these beta hats. So at the very last iteration. And what we can see is that we have a very, very steep line. So that means beta hat 1 is obviously greater than 0, but greater than 0 by a lot. And in fact, if I were to continue this iterative process, this beta hat 1 is going to continue to increase. This corresponds to what I said before, that essentially that is going to positive infinity. So why does this occur? Well, hopefully it makes some intuitive sense. If I have all zeros for x1 less than or equal to 5, all ones for x1 greater than 6, well, yeah, I want to try to fit something that really distinguishes between the x's, between the possible values of x's relative to y. And what does that? Essentially a vertical line. Now, what if you actually did increase the maximum number of iterations? I did that. And what do you know? I got convergence after 26 iterations, or R calls it convergence. This essentially is the problem with using the residual deviance to measure convergence, because in fact these beta hats will continue to change. So if you change the epsilon to something that's even smaller, you will see a lot of different, you'll see these beta hats continuing to change, indicating that there wasn't convergence. So the main thing to get out of this is that R is not perfect in determining if convergence occurs or not. And so sometimes you need to actually do some investigations on your own by increasing the maximum number of iterations, by changing the epsilon to see if truly convergence has occurred. Now, what if we change the y values for x1 equal 5 and 6? So let's say at x equal 1 equal to 5, we have y is equal to 1, and at x1 equal to 6, we have y equals 0. So those are the changed observations. Then I do not have complete separation anymore, and my model is estimated like normal. Everything works out. I do have convergence. So what if you do have complete separation? What can you do? Here are two possible options. One could use what's called exact logistic regression. We've seen some exact inference procedures before, and basically this is an extension of those ideas now to a logistic regression setting. Typically most semesters when I teach this course, I do not cover this specific topic, but I do have a section in my book that does talk about it if you're interested. Another possibility is to modify the likelihood function so that as these, what's happening with maximum likelihood estimation, why we don't have convergence, is that the likelihood function keeps on going up and up and up and up. Well, maybe you can modify the likelihood function by putting a penalty on it, so that once it keeps on going up, it's going to moderate the likelihood function. It doesn't, and prevent it from continuing to increase. And so that's what one could do. There are a number of different penalties that one could use. For this particular situation, one by Firth works rather well. If you're interested in the details, take a look at my book. So some final comments here. Now, complete separation, based upon what I've said here, you might think, oh, that's a really bad thing to happen. But in some situations, it's not. Let's say your goal is to distinguish between the y equals zeros and y equal ones. And if you have complete separation, well, congratulations, you can do that perfectly. And so in that kind of a setting, complete separation is okay, in fact, desirable. But if you want to understand, let's say, the relationship and measure it like with an odds ratio or estimated regression parameter, you will have problems when complete separation occurs. Sometimes complete separation can occur through a combination of two or more explanatory variables. In that particular case, one's not going to be able to do one of those simple plots like I just did there. And so that obviously can cause a problem. And so what one will have to do is rely on some of the warning messages that R produces to help you start to suspect that there might be complete separation. Now, there may be even times when the GLM function doesn't provide any kind of warning. And what you can do in those particular situations is that when the regression parameter estimates are very large or very small, and you also see very large estimated standard deviations, or in other words, I should maybe put standard errors there. What that is indicative of is that there is a convergence problem. And so if I were to see something like that, immediately what I would do is decrease my epsilon to see if my regression estimates are changing with a stricter convergence criteria. And if they significantly change, then that is a warning to me there's a problem here. This is actually, I have non-convergence. Okay. So then that concludes this small section that gives a little bit of more details about the iterative numerical procedure that R does to find the maximum likelihood estimates, and also gives information about this problem that can occur called complete separation.